So welcome at session 5. In this session, we'll learn about the activation function or activation functions, which are the one of the building bricks of neural network and artificial neural network. We have seen so far two examples of them. The threshold activation, which is inspired by the biological neurons, which basically represent the idea that when energy comes into the neuron, then when it reaches a specific level, the neuron would fire. We have seen also the sigmoid function as a part of the backpropagation. It was just an example of how to calculate the derivative of that part of the chain model, but we'll see today more activations functions that can be used within the neural network. What are the advantages? What are the disadvantages of these activation functions? So starting by the threshold function, we have said that the idea that we have inputs, dendrites in the biological neurons, that when they basically some energy there, when it reaches a specific threshold, then the neuron actually would send that output here, which means biologically it would fire. Now, when it comes to backpropagation, when it comes to gradient descent, we cannot use the threshold model here or threshold neuron here. Why? Because it's non-differentiable function. We cannot differentiate it. It is a discontinuous function here, which means that this part of the chain model that we had in the backpropagation lecture, we cannot do this part. So this chain model here would break, and we cannot do the backpropagation. We cannot train this new network using backpropagation. This is why basically researchers had to actually model kind of approximation, mathematical approximation of the step function or the threshold function, which is here the sigmoid function. And the sigmoid function has basically this, as I have seen in the backpropagation, has this mathematical model. It is exponential here down, and it has this basically shape. It looks like the step, as I said, but it is smoother, and it's differentiable. And it also has another feature which basically it represents probability, because the value of the sigmoid is between 0 and 1, and the higher the value is, that means the higher confident the net neuron is about its output. For example, if it is 1, that means it reaches a saturation, it reaches the highest, let's say, probability. And when you have seen, for example, in the classification samples where we had basically the decision function, and we said if you are at the decision function, at the decision line, for example, then the model is 50% sure about which class it belongs to this point. If the point is to basically, the further the point is from the decision function, that means the higher the output is of the sigmoid function, for example, that means the system is more confident about this point, that it belongs, for example, to class A or class 0. And for example, in here in this threshold function, we don't have this feature, because the threshold function, if you are at the line, then okay, probably it would directly put here value equal to 1. If you are before the line, it's 0. It doesn't tell you how far you are from that decision line. And this is a good feature of a sigmoid, because we can do that, because it's basically starts from 0, then it's here it has a kind of exponential growth here, and then it starts to smooth down, and here we have the saturation. So also good feature of sigmoid, it has an easy first derivative that we can use it in the backpropagation, as we have seen in the backpropagation feature lecture. So it's mainly used to predict probability. It can be used as an output layer and as a hidden layer, which means as an output neuron and as a hidden neuron. When it is in the output, when it is an output neuron, usually we are talking here about binary classification, which means, as I said before, binary classification means it is 0, 1. We have two classes only, red apple, green apple, banana, or apple. So it has only two outputs that we are trying to train machine learning to predict. So in this case, we can use sigmoids, and the sigmoid here basically would be saying if it is, for example, the higher the value of the sigmoid output is, it's more banana, for example, and the lower it is, it's less banana and more like an apple. So this is basically how we can use a sigmoid function here as an output. As an input is like any hidden neuron. Basically, as we will see later, the neuron in the hidden layer usually represent specific feature of the input or of the layer before. And when the higher the value is here, the higher the feature is. Let's say we have a neuron at the first, let me go very fast down here. Let's say our input here is the color of an object, shape, size. And we are trying to classify now between banana and apple, for example. And the third something like, I don't know, strawberry. So the color here, this input is a color. And as I said, this shape, this size. Now this neuron has one function. It has learned one function. When it sees the color yellow at the input space, it would send a signal, it would fire. The more the yellow the color is, the higher the output of the signal would be. The lower the yellow, the lower the value of the output is. So this neuron looks only at the yellow color in the input image. It doesn't care about anything else, doesn't care about shape, it doesn't care about any other features. This neuron learns to look at the color. For example, this neuron would learn to look at the red color, or would learn to look at the shape. So each neuron in the neural network should learn one specific feature or the distinct task or distinct feature. And the more when we talk about sparse, the more sparse the neurons are. Sparse means that actually each neuron learns one feature. We don't have redundancy, which means we don't have two neurons that has learned this, or they have learned the same feature, because that means we are doubling the calculation. That means we are using more computational power and more memory. So this is the functionality of sigmoid. As I said, the higher the value is, the more confident the sigmoid or the neuron about its feature. It has, of course, some, basically here we have some cons, or we have some drawbacks of that. It has sharp dump gradient during backpropagation. So basically, because of this here, the growth here, and you can see here the derivative there, the first derivative of that sigmoid function. We can see that here we have really sharp derivative, which means sharp gradient could lead to big steps. And the problem is that in these regions here, so it's either sharp or very low gradient. Very low gradient means that we are actually not learning anything. So that means we are reaching a zero gradient. That means the neuron actually, which are important parts here, because this is how confident the system is. When it comes to these two regions here, it has very low gradient, which would lead to gradient vanishing, as we'll see later, would lead basically to slow convergence as well, gradient saturation, and slow learning in general. And also the problem of the sigmoid function is basically asymmetric, because here we have the value between -10, for example, and 10, and here between 0 and 1. So it's asymmetric around 0 when it comes to the output. When we have asymmetric activation functions, that means you have asymmetric loss function at the end. So this basically would lead to asymmetric loss function. For gradient descent, because we are looking to the minima, as we have seen, and if the function is symmetric, like we see here in the red one, it's easier to find the minima. If the function is asymmetric, like the blue one here, it's hard to find the minima. So it's always, when it's convex symmetric activation, symmetric cost function, it's always easier to find the minima, which means the learning would be much easier. Because sigmoid is asymmetric, it also adds more challenges to the learning. So now, gradient vanishing, which is here basically one of the main challenges of neural network in general, deep learning in general, but sigmoid basically more specifically. what is the idea of gradient vanishing? So forward and backward propagations involves many multi successive multiplications. We always have multiplications. We multiply input features with the weights, and then we take the output of a neuron, we multiply it again with another weight, and also so on. So we have many successive multiplications in the forward propagation. Let's say this is the input, or this is the first hidden neuron. Then we are going deeper in the network, and we're doing a lot of multiplication. Now, mathematically, if we are multiplying with between numbers or many numbers that are smaller than 1, that would lead the value to vanish because we are going closer to 0. And you can see that here. So, for example, we have 0.9, then we multiply. So all the values here are smaller than 1 because the sigmoid output is smaller than 1. And the weight would be smaller than 1 if we do some also regularization, as we see later. So basically, this would be smaller than the 1, smaller than the 1, smaller than the 1. And if we multiply, for example, 0.9, then we get 0.9 multiplied by 0.4, which leads to 0.36 multiplied by 0.2, 0.07 multiplied by 0.5. We have here 0.03. So basically, the knowledge has vanished, or the activation vanished. It likes basically in real life, if you have if these are actually personas or persons, and I'm telling something to the other, and the other telling something to the other. And sometimes when the knowledge or the information would actually would be changed, first of all, when it's basically it's transmitted from one to the other, and sometimes it vanishes. Now, what is important for the learning is the gradient, which has the same problem. If we have now gradient, because the gradient also of the sigmoid is much lower than the activation itself. And here, for example, it could be 0.3 and max 0. Actually, max is 0.2. But let's say with some multiplication with the other weight, it would be 0.5. Then here also we have multiplication with small numbers in the back propagation now. Then for the first layer, we would have very low gradient. What's the meaning of very low gradient or gradient goes to 0? That means these weights are learning nothing. So the deeper the network is, the harder it's to learn the first layers, because the first layers actually are not receiving that high gradient, so they are not receiving that high basically feedback to learn. And this is what's called the gradient vanishing problem. So sigmoid has this problem because the output of sigmoid is between 0 and 1, so the values are smaller than zeros, and also the gradient, the derivative also is smaller than even 0.2. Now, when it comes to the second activation function, so we need to solve one issue of the sigmoid, which is the basically asymmetric loss function. So this is why first they introduced the basically tan h, or it's called the hyperbolic tangent function. And it looks the same, but here basically it's centered around 0. So the tangent function starts from -1 to 1, not from 0 to 1. That makes basically the loss function more symmetric, or symmetric actually, and that makes the convergence and learning much easier and much faster. So we have better training performance and faster because it's 0 centered. Also, it's basically let's say if we're talking about values between 0 and 1 and probability, 0, 1 means more like binary, more like logic. But if we are talking about universal function approximation, it's not only logic, which means not only 0, 1. That means we need to have a kind of range of values between, let's say my data set is about temperature. And the input temperature is between, in my data set, let's say between -50 and 50. So what we could do in this case, we can now scale it down to -1 and 1 and use it with this neural network. So it should symmetry here is very important when it comes to numerical data and continuous data. Now this is basically the tan h or the hyperbolic tangent function. This is how it looks like. This is also its first derivative is easy, not that bad, not that hard actually. We can include it in the backpropagation. Now, of course, the tan h could not. It's better when it comes to gradient vanishing, because the gradient is generally bigger. The gradient of sigmoid is very low, 0.2, as I said, the maximum. Here it's higher, but still have this problem at the saturation levels where it actually has zero gradient. So this basically was not solved. And actually, yeah, so the next part then, or the next activation function, is called soft sine function. Now, soft sine function is also kind of approximation of the tan h, or a different modeling of what is the tan h trying to do. It used more like a quadratic polynomial. It is smoother than tan h. This is basically why it's sometimes better, because tan h has here this kind of exponential growth, which is kind of large step. And here basically this causes a problem in the learning in the gradient, because here we have high gradient for this area. And also, for example, when you have this large step, we cannot distinguish between different features or different classes, because the values here actually are, let's say, the steps here are too big. So we need actually to have to smoother function to do that. And smoother function also is better for the gradient. Always, the more the function smoother is, or then the gradient or the cost function would be smoother. That's good. Smoother cost function is, or the loss function is basically then the gradient descent or the backpropagation in general would be better, or would perform better. It still have basically a vanishing gradient problem, obviously, because we still have here the threshold, but it is better. So it is better in this case than the also the tan h, because here it's also the transition is smoother than in tan h, which we see it here is much basically sharper, which also would be translated in the gradient or the derivative, because the derivative also would also go smoother from the highest to the lowest. Here it's more sharper, so it's basically the derivative is either too high or too low. Okay, so always smooth means better for the gradient descent for the learning. Now we still have problems of gradient vanishing, and we still have problems basically because of this saturation parts of the either sigmoid, soft sine, or tan h. This is why the rectified linear unit is introduced, what's called ReLU. Is now one of the most common actually activation function. It's actually now the first choice always to use. It's first of all because it's very simple in terms of calculation, so it's much easier to calculate the output of the ReLU. That means when it comes now to implementing your network to let's say build hardware, or let's say hardware of your network, then it's much easier to use ReLU than sigmoid, because exponential operations and multiplications are hard to implement in hardware. That's why, for example, ReLU is the best choice now to use. For example, Tesla, they built their own neural network hardware, and they built ReLU as the activation function because it's, as I said, much faster. By much faster, I mean now it's also less, basically it needs less computational power and less energy for sure as well. So the ReLU function is very simple. It's basically max between 0 and x, which means if the value here is smaller than 0, then the output is 0. If the value is bigger than 0, then the output is x. So it's a line, linear. In this way, we don't have the saturation. We don't have this basically the problem of the vanishing gradient, because here we don't basically limit the values to be between 0 and 1. And as I said, it's easier in terms of calculation. But of course, it does still have some issues. For example, ReLU also is asymmetric. So we solved one issue, but we still have the other issue. And also ReLU is much faster, and because it doesn't put, let's say, constraints on the functions like in sigmoid or like in tanh. Like constraints, I mean by try to limit the output to 1, maximum output to 1. That would lead to overfitting. So we'll see later in the regularization part, the less the constraint we have on the network, the higher chance to go to overfitting. So this is why ReLU could actually end up with overfitting. It has the idea of dead neurons, or the problem of dead neurons. What's the meaning of that? Basically, if when I initialize my network with random weights, if basically the output, or actually the pre-activation model, which is the model that would be applied at the activation function, is in this region 0, that means the neuron is dead from the beginning, but the output is 0, and that would lead, for example, to let's say this neuron would never be active again in the learning because it's always 0, so it will learn nothing. We would have this neuron within our network, which is kind of redundancy, has no feature, has no role, and this is what's called the dead neurons. Now, one good feature of the ReLU, it has basically static gradient. So it's basically, it has here basically the gradient, which is very simply it's equal to 1 always. So it's basically stable gradient. Dead neurons, as I said, one of the disadvantage. It's faster in computation, but it could lead to overfitting, and it could lead to gradient explosion. The gradient explosion is the opposite of gradient vanishing. The issue here basically now, if we are doing multiplications with values that are over 1, then that would lead to large numbers, and that would lead to explosion in the activation and explosion also in the gradient. The same idea, because ReLU, as I said, doesn't add any constraints on the output, so if the output could be 1000, no problem. And if we do that, for example, something similar with but now with bigger values bigger than 1, multi-successive multiplications would lead to high activations, but also would lead to very high gradient. High gradient, that means big steps. The iteration we do to the weights. Big steps means you might miss the minima, local minima, or might you actually not only miss the minima, basically you might move to another minima, to another part of the loss function, or you might miss the loss function at all. So the neuron would die, as I said, from these big steps. Now, because of the problem here that, as I said, we solved something, but we still have here in this region the dead neurons. We have 0 gradient, so that also means no learning here. Some researchers, they introduced the leaky ReLU. The idea of leaky ReLU is basically that they add here small leaky parts, which basically, now if it is x smaller or equal to 0, then the value is ax, not 0. And that we see basically here. That means that it would have very small gradient there. So a very small value there. It's not 0, but it's very small. In this way, basically, the neuron would not be dead. It would learn. It would learn slowly, but it would learn, so it won't be dead. The overfitting could still happen. The gradient explosion could still happen because of that. We will learn later how to avoid gradient explosion and how to avoid overfitting using regularization. But in general now, ReLU and leaky ReLU are much better than sigmoid because they solve most of the problems. They still have these 2 issues, but they are not, we can solve them with other techniques. And they are very commonly used because also, as I said, the needed computational power is much less than other activation functions. So this is a comparison, general comparison between the activation functions starting from the sigmoid, which is between 0 and 1. Tan H is between -1 and 1. The soft sign basically in green is smoother than the tan H, so it doesn't have this sharp exponential growth here. The ReLU, which is basically as the leaky ReLU, but they have here small difference between them. Looking at the gradient of them, we can see that first of all, sigmoid has the lowest gradient. That's why it's more likely to end up with gradient vanishing. So because of that, the tan H basically has a high gradient, but it's also sharp gradient. The soft sign is as the tan H again, but the smoother gradient it has. Now ReLU, it has a stable or static gradient which equal to 1 always for the network, but it has a 0 gradient in this region lower than 0. Leaky ReLU is basically the same as ReLU, but here it has a static gradient equal to alpha usually. Alpha is a value that here we are multiplying with x. This value is between 0 and 0.1 usually. And sometimes could be adaptive, so it could be also learned. Now another activation function, which is now only for the output neurons and merely for multi-class classification problems. This is called softmax. So it is used to compute probability distribution from a vector of real numbers. What's the meaning of that? If I have multi-classes, let's say I have 5 classes. Now something to basically now to put in your head that when I have, for example, 5 classes, so I have classification problem with 5 classes or categories, the network should have 5 outputs. So the number of output neurons is equal always to the number of classes. Now what softmax does is basically convert these 5 output neurons to probability distribution. The neuron that has the higher probability, let's say neuron number 1 represent car, and neuron number 1 has a value of softmax value equal to 0.9. That means it's 90% sure that this input belongs to car. The rest would have values that, for example, equal to 0. The rest basically, the sum of the rest should be equal to 0.1. So the sum of the output of the softmax layer, the sum of the output of these 5 neurons should be always equal to 1. Okay, it's a probability distribution. And it has this mathematical function. So it is basically here the exponential part is just to increase the values between the outputs, as we'll see now as an example. And here's just kind of normalization. So what we are doing here, we are doing normalization of the output. So I here is the neuron output index. And for example, for first neuron, we are taking the exponential of the output of that neuron divided by the sum of the exponential of all other neurons. The difference between sigmoid and softmax, sigmoid is used in binary classification, while softmax is used in multivariate classification tasks. Here we have an example of how softmax works. Let's say we have 3 features in your network, 2 hidden layers, 2 neurons per hidden layer, and here is our output layer. Usually when you see a softmax at the output layer, basically it's a combination of these two basically layer, but here one-to-one connection. The first part is a linear function. When I mean linear, that means there is no activation function at all. It's only the pre-activation model, which is a summed weight of the inputs, or the weighted sum of the inputs. And let's have example. For example, we get an input, and the linear output here is 98, 150. And if I look at this basically now in terms of classification, it's hard to decide what the meaning of that, because they are unnormalized numbers. They don't. It's easy to know that this one is more. We are more confident about this one because the value of this one is higher. Let's say this is apple, banana, and strawberry. Then the system is more confident that it's basically banana because it has a higher value. But we need to see that in terms of probability or confidence, and this is what softmax does. So if we apply the softmax function here, the exponential of 98 divided by exponential of 98 plus exponential of 100 plus exponential of 50, we get 0.1, which is 10% basically confident about this neuron. Then if we go here, this should be actually the on one, not this one, because it has the higher probability. I'll just correct it. Then here you see basically it's 198, 100, 150, then it's 90% sure about this neuron. So it's actually 90% confident that this is a banana. For this one is very low confident, it will be 0%. So this is how we convert the output of the linear output or linear functions here to a normalized probability distribution using softmax. That's why I said whenever it comes to classification, multi-classification problem, first of all, the number of output neurons should be equal to the number of classes, and there we need to use softmax. If we have binary classification, only 2 neurons, that means we can use their sigmoid. Okay. Here there's a comparison between now the sigmoid function and the other activation function, just to see where the gradient is vanishing and how it vanishes. So here we have basically a deep neural network consists of 12 layers. So basically this is the index of layers here. This is the training iterations. So the deeper we go in this direction, the more iterations are happening here. What we see here that at the beginning we have, this is basically the value of this color here is the gradient value. So the more reddish it is, the higher the gradient is. The higher the gradient is, basically the higher the feedback is from the output, which means we need to learn something. But what we see here, for example, first of all, along the epochs, nothing is changing, although iteration isn't changing because it has the same color always. The problem here, basically what's happening is that the backpropagation is vanishing. So the gradient from the first, which was very high, basically comparing to the other, 0.01, it ends up close to 0. So basically the gradient vanishes. That means these neurons actually here, most of these neurons will learn nothing because they are very small gradient. And because it's learning nothing, basically, this is why here nothing changing between the iterations. It's nothing basically has been improved there. So here I'm just going to the live dashboard here. I will put the link to it here just to see basically how the gradient is vanishing there. So it's becoming very much smaller. Okay. And this is basically for the sigmoid. Now, if we look at, for example, the tanh first, let's look at the tanh. Of course, the tanh has better gradient, because it has in general higher gradient than the sigmoid function. It's more symmetric, which means the learning would be easier. We won't end up with vanishing. And because of symmetric, also we won't end up with vanishing. And for example, if we look here at the first iteration, we have relatively high gradients from the beginning to the end. This gradient basically becomes smaller and smaller. That is not an issue. That should happen actually when we go with more iteration, that the gradient should become smaller and smaller. That's because we are converging at the minima. So when you converge at the minima, the gradient will reach 0. And if we have actually this kind of radial phenomena like we see here, which means by radial I mean this basically the first point here is too dark, and comparing to the first the upper left point here, which is the lowest value, this is what is the radial I mean there. And here basically the tanh is doing well. What is interesting, if you look at ReLU, we can see it has a kind of opposite or symmetric comparing to the tangent. What is the reason here? As I said, ReLU at the beginning could have dead neurons, which means at the beginning it's hard to learn. It takes it's a few iterations until the learning starts. So it's because of the dead neurons at the beginning, that neurons are on the left, or they have the values, input values smaller than zeros. That means that would lead to ReLU smaller than 0. But for example, in general, ReLU have, so that means, for example, ReLU is still learning after 5 iterations, and we can see it is different from tanh. We don't know here in this case if what happened here, the gradient vanished because we actually ended up at the minima, or because we had the gradient vanishing problem, which means that we stopped learning because we had very small values and there's no, we cannot improve more. That is not happening obviously with ReLU, because ReLU is still learning. We have like a radial again here phenomena, but is an opposite radial phenomena comparing to the tanh. So there are other activation functions that I didn't talk about, but there are many activation functions. I talked about the most important ones, and the others actually are just kind of they are the same as ReLU, softmax, and so on, but they have some changes there. Like we have seen leaky ReLU, for example. There's also soft plus, which is another activation function like we see here, but still has the same problem as a sigmoid. We have ELU, which is also kind of adoption of the ReLU function. It's obviously better when it comes to the dead neurons, as we see here, because start learning from the beginning. So this is about now the activation functions. As I said, now the best option to start with ReLU or one of its childs like ReLU or leaky ReLU, because they are the most common. They are better in performance in general. They recorded higher accuracy, higher performance, easier in the computation also, and still have some problems, as I said, like explosion and overfitting, but this we will solve actually later with the utilization and other deep learning techniques. Thank you.